So let's see how semantic analysis is performed by a compiler. So semantic analysis takes the parse tree, performs semantic analysis, and it will output a semantically correct parse tree. If the inputted parse tree is not semantically correct, then it will output the logical errors or type checking errors found in your program, in your expression. So semantic analysis basically checks for type errors and performs error correction, logical error correction. For example, if the input is like this, a of 10.5, so this expression is syntactically correct, but logically we can say that it's incorrect because the array index cannot be a real number. It can only be a whole number or an integer number. Similarly, when you take an expression like this, c is equal to 4 plus 3 into 60.0. So 60.0 is a real number. So when you perform, this expression seems to be syntactically correct, and when you perform 3 into 60, this 3 has to be converted into real, then only we can perform multiplication. And when you perform addition, this real value, this integer value has to be converted into real value and perform addition, and then the real value should be assigned to an integer value. So some implicit typing errors, type conversions has to be done. That will be done by the semantic analysis phase. So how the semantic analysis phase performs this type checking and logical error. So for that, the semantic analysis phase uses the concept called syntax directed translation. In short, we call it as SDT, syntax directed translation. So using this syntax directed translation, the given syntax is checked for any semantic or logical errors or type checking errors. So how this SDT works. So let's see what an SDT is. So SDT is nothing but it's a context-free grammar. In addition to this context-free grammar, semantic rules will be attached. So we'll be having a set of grammar like E derives E plus T, T derives E, T derives T into F, T derives F, derives number or ID. So this some of the grammars we have studied. So there will be a grammar like this, and attached to this grammar there will be some semantic rules. The semantic rules corresponding to the actions we have to take. So I will show an example how an SDT will look like. So this is an example for an SDT, syntax directed translation. So this is the grammar. So I have already said attached with each grammar, attached with each production, there will be a set of semantic rules. So this is the grammar here. So you are familiar with this grammar: E derives E plus T, E derives T, T derives T star F, T derives F, F derives number. So these are the productions which we are familiar with, and to this production I have attached some semantic rules. So with this production, F derives number, F dot a number value will be assigned to this F variable, and a value will be assigned to this T variable. So what is this production? Whatever value in T will be multiplied with the value in F, and that value will be assigned to the variable T. So here how to attach the semantic rules. So when you write the semantic rules, we can attach an attribute value to the grammar symbol. So in this grammar, what are the possible symbols of various symbols here? L is a symbol, E is a symbol, T is a symbol, F is a symbol, and number is another symbol. So these are the different symbols. So attached with each symbols, we can attach an attribute value. The attribute value can be anything. It can be simply a value of that variable. It can be a scope. It can be type. It can be a pointer, like a memory location. It can be its so it can be a number. So these are the different attributes we can attach with the grammar symbol. So here in this SDT, syntax directed translation, we are taking the attribute value. Value is the attribute we are taking. So there are other SDT where we are considering the attribute type. Here the type of here this is the production. So T, D, L are the different symbols here. So for these symbols we are considering the attribute type. So these are the various attributes that can be attached with the symbol. So we are taking the very first simple example. So here we are taking the attribute value. So what does this production means? Whatever number you have, whatever be the lexical value for the number you have, that should be assigned to the value attribute of f. So when you see a production like this t to f, what happens? Whatever value this val attribute have in f, that has to be given to the assigned to the value attribute of t. So taking this production, what is this corresponding action? So whatever value f has, that has to be multiplied with the value of t, and that should be assigned to this t. So here there will be a confusion which t's value should be used for multiplication, whether this t's or this t. So I just put a t1 here. So that it means the value of t1 should be multiplied with the value of f1, f, and that should be assigned to t. Similarly here what happens, t's value will be assigned to the value for e. So here the value of e will be added with the value of t, and the result will be given to the value of this e. So there is also a confusion which is value is added, whether this is or this is. So I just to avoid confusion, I written a dash here, a 1 here. So now it's clear, e1's value is added with the t's value, and the result will be given to this e's value. And here what is the action to be taken? So when you find such a production like this, you have to print the whatever value you have in e, that has to be printed. Okay. So this is an example for a SDT, syntax directed translation. So attached with grammar, each grammar there will be a set of semantic rule, and the semantic rule has to be executed, or these actions has to be performed when you find a reduction like this. Let's see how it's done. So SDT, as we said, there will be a grammar, and attached with the grammar there will be a set of semantic rules. So there are different ways we can represent and notations for performing syntax directed translation. One is syntax directed definition, and other is a translation scheme. Let's see the difference between SDD and translation scheme. So these are example for a syntax directed definition, SDD. So let's see how this SDD works, how we can perform this semantic analysis. So there I have given a small example. So this is the input, 3 plus 5 into 4. Now the first thing is we have to construct the parse tree. So this is the grammar. Based on this grammar we have to construct the parse tree. So the start symbol is L derives EN. So L E small n, and from this E I am taking E plus T, so this is the syntax tree I have derived for this input from this grammar. Okay, so here the number is 3, 5, 4. So 3 plus 5 into 4n. So this is the parse tree for this given input based on this grammar. Now next is how to perform the semantic analysis using this semantic rules. So this parse tree is evaluated top to bottom and left to right. So it's evaluated top to bottom and from left to right. So let's start from this start symbol S. So this is how. So L gives a production E plus E dash, and E gives E plus T dash, E plus T, and from E T, T to F, and from F to num. Now we are, and for this number I have given the lexical value of 3. This is given from in our input. So from here I am going to the reduce step, that is F to num. So we are going from num to F. So we are reducing this number to the production to the symbol F. So when you perform a reduction from number to F, we have to perform this action. So what is this action? Whatever value in the number, that has to be assigned to the value attribute of F. So f to num, that means the whatever value in number, that will be assigned to the value attribute of f. So f dot value attributes gets a value 3. Now again I am going back. So it's a t to f, which means there is a reduction from f to t. So t to f. So reduction from f to t. Then you have to perform this action. That is, whatever value in f, that should be assigned to the value attribute of t. So t gets a value 3. So f dot value has a value 3. So t dot value gets a value 3. So I am now tracing back here. There is another reduction. T is reduced to e. So whatever value t has, that has to be given to the attribute value. So e dot value is 3. Now I am again going back. So this again t derives. T star f is another production. T to f is another production. Now number gets a value 5. Now I am going back. So this is a reduction. So f to num means number is reduced to f. So the attached semantic rule is f dot value is dot number. So f dot value gets a value 5. And now again I am going back. T to f, that is f is reduced to t. So the attribute value got the f dot value, which is 5. Again I am going back. So here again the reduction number to f. So f dot value gets 4. So I am going back. I came here. That is, t is expanded to t star f. Now when I reach backward, what happens? T star f gets reduced to t. So t star f is reduced to t. So what happens? The value in t must be multiplied with the value in f, and that should be assigned to the value attribute of t. So t dot value gets t dot value into f dot value, that is 5 into 4, 20. So I reached here. So this is another production. E derives e plus t. So what is there in e derives e plus t? The value of e is added with the value of t, and the value will be obtained, added value will be given to the attribute of e. So e dot value gets e dot value plus t dot value. So 3 plus 20, 23. And it goes like this. It comes here. That is L. So we started from L. At the end we reached here. So L derives En. So En to L will be a reduction. So what is the action to be taken? Print E dot value. So whatever value in E, that has to be printed. So the output will be 23. So this expression is syntactically and semantically correct. So we got the output as 23. And let's see another example. How this STD is performing. So this is another example for an STD. So we have a set of production like this. E derives E plus T, E derives T, T derives T star F, T derives F, F derives number. So here we can see semantic rules is not given for every production. Only for E derives E plus T there is a production. T into F there is a production, and F derives number there is another and the semantic rule. So there is no semantic rule attached with this production and this production. So let's see. So this is the FDD for SDD for converting infix expression to postfix. So this is the input. So after attaching the semantic rule, we will get the postfix expression. So let's see how to obtain the postfix using this semantic rule. So 2 plus 3 into 4, using this production I have to draw the parse tree for that. So starting from E plus T, from E to T, from T to F, and F to number. The value is 2, and plus after T, T star F, again from T to F, F to number, I got the value 3, and F2 number, I got the value 4. So this is the parse tree for the given input from this grammar. Now I have to attach the semantic rule with this. So we evaluate from top to bottom. So starting from here, this is the expansion. So no need to apply semantic rule. So comes here. So this is a reduction, F2 number. So it's a reduction. This number is reduced to F. So we have to write this. We have to perform this action, that is print number dot lexical value. Whatever there in the number, that has to be printed in the output. So the output will be first. The value is, the output will be, it will print 2. Okay, so there is no attribute value attached with the symbol. E has no attribute value. Just we are printing it. So now again come back. This F is reduced to T, but F is reduced to T. There is no semantic rule attached with it, so we can move forward. So E to T, from T to E, from T to E, there is no semantic rule attached. So again we are moving. From top to bottom and from left to right. So there is a reduction, that is from number to F we are reducing. So print the number lexical value. See here the number lexical value is 3, that will be printed. And again there is a reduction, F to T, there is no semantic rule attached. So we are again moving. So there is a reduction, number to F. Attached rule is print the lexical value. Here is 4. 4 will be printed. And when I comes here, T giving T star F. That means T star F is reduced to T. T star F is reduced to T. So what we have to do? We have to print star. Now I am going back. Reached here. So E derives E plus T. E derives E plus T. That is E plus T is reduced to capital E. So we have to print plus. Plus will be printed. And our process stops. So what is the output? 2, 3, 4 star plus. So this is the postfix notation for the given infix expression. So using the semantic rule, we obtain the postfix notation for this infix. So this is an SDD, syntax directed definition, for converting an infix expression to the postfix expression. So let's see one more example, so that so you will be familiar with the concept of SDD, syntax directed definition, how this production rules are, semantic actions are performed. So this is the input and this is the grammar, and attached with this grammar some semantic rules are given. So let's see how to perform this semantic analysis. So this is the input, so we have to obtain. I am going to draw the parse tree. S derives X, X, W, and from W S, Z, small letter Z, again S, X, X, W, W2, S, Z, and from this S, Y. So hope our input has obtained, that is XX, 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 Y, Z, Z. So this is our input. So let's see what is this semantic rule gives. So we evaluate from top to bottom. There is no reduction here. This is our expansion. There is no reduction here also. So it's a reduction, that is Y is reduced to S. So what happens? We have to print 2. So the output will be 2 will be printed. And going forward, now W derives Y Z, W derives capital S, small z. So S Z is reduced to W. S Z is reduced to W. So we have to print 3. Here S is derived to XXW, which means that XXW is reduced to S. XXW is reduced to S, so you have to print 1. So W derives SZ, which means that SZ is reduced to W. SZ is reduced to W, so we have to print 3. So this is 3 here, not Z. So again the process completes and comes here. So S derives XXW, which is the first production, and the semantic action as attached with this 1. So we have to print 1. So this is the output for the given input. So this is the input, this is the grammar. First we have to draw the parse tree, then we have to decorate the parse tree. This is called decorating or annotating the parse tree to obtain the output. Okay, let's see one more example. So this is the grammar and the semantic rule attached with it. So this is the input we have to obtain. Let's see how to obtain the input from this parse tree from this input. So we starts with D, T, L and T2 real and L comma ID, and for this L I have written the value. So what's the value of ID here? It's A, and for ID it's B. Okay, so let's see how it works. So evaluation from top to bottom and left to right. So I am annotating or I am decorating the parse tree like this. So here T to real. That means from real to T there is a reduction. From real to T there is a reduction. So what is this semantic rule attached with it? Action we have to take. Here type is the attribute. So real value should be assigned to the attribute, type attribute of T. So T dot type gets the value real. I'm moving. So L to ID. L to ID, that means ID is reduced to L. ID is reduced to L. So add type ID dot entry comma L dot type. That means this ID dot entry we have to enter this entry into the symbol table. Along with we have to enter the type of L. Whatever be the type of L, that has to be entered along with the ID entry. So in the simple table we have to enter A and we have to enter the type of L. So is the type of L known? No. Till now the type is not known. So I just simply write L dot type here. Once I get the value of L dot type, that will be updated here. So I am moving forward. So there is a reduction. L comma ID is reduced to L. L comma ID is reduced to L. So here it's a reduction step. So here what happens? Whatever be the type of L, that is this L type, whatever value of this L type, that has to be assigned to this L1. But this L type's value is also not known. Then only we can assign to this. Okay, so this L value, this here L is this and L1 is this. So this L value, L type of this L is not known. So once this type of L is known, that will be assigned to this type of L1. And also there is another action to be performed. You have to add the ID, that is here the ID is B. So you have to add the ID B into the symbol table along with this type, L type, which is unknown. So whenever I get the value of L type, that has to be entered here. Now coming to here,